Today we're going to talk about section 2.7 in our BJU Press Pre-Calculus textbook. We're going to be going over how to graph polynomial functions and just some characteristics that are important to know. So we're going to graph and discuss the characteristics. We're going to identify what we call relative extrema, which might be something new. So we'll go over what that means. So when we're talking about polynomials, domain, which is our x values of polynomials, is always all of the real numbers. And polynomials are always continuous. There's never going to be any jumps, gaps, or holes. So when we say continuous, that means that if we were to trace the graph with a pencil, we would never pick up our pencil. Polynomials are also smooth curves, so they don't have any sharp points like absolute value graphs have. They're always going to be smooth curves even when they change direction. And since polynomials are functions, they have to also pass the vertical line test. So here's an example of a polynomial function, 1/4 x squared. If you notice, our leading coefficient is positive, and our degree of our polynomial is even because our degree is 2. So that means that the graph approaches from the second quadrant and leaves from the first quadrant. X cubed. So for this, our leading coefficient is positive. It's actually a positive 1 because there's an invisible 1 there. And our degree of our polynomial is odd because it's a degree 3. So it's going to approach from the third quadrant and leave from the first quadrant. Now let's look at negative 1/4 x squared. This is very similar. The only thing that we changed is that the leading coefficient is now negative. And our degree of our polynomial is still even. So now we're going to approach from the third and it's going to leave from the fourth. So now let's make that degree 3 have a negative leading coefficient. And so that means that we're going to approach from the second and leave from the fourth. So anytime that you put a negative, it kind of switches from what the original looks like. So exploring all of these, changing all of these and looking at the differences, based on all of that information, we can kind of come up with an always, never fails chart on when to know when we're going to go up and we're going to go down. So we're looking at a chart where we are looking at leading coefficients, either positive or negative, and the degree of the functions, evens and odds. So when you have a leading coefficient that is positive and the degree of your function is even, that means both tails are going to go upwards. If you have a leading coefficient that's positive, but you have an odd degree, your left tail goes down, so it's coming up from the third quadrant, and your right tail goes up, so it's leaving from the first quadrant. If you have a negative leading coefficient and an even degree, both tails go down, so it's coming up from the third quadrant and leaving through the fourth quadrant. However, if you have a negative leading coefficient and an odd degree, your left tail is up and your right tail is down. So it's coming in from the first quadrant, but then it's going to leave in the fourth quadrant. So the ends of the ends, or the tails, is what this chart called them. The tails, or the ends, of the polynomial graphs always approach infinity, or negative infinity. So let's discuss the tails of this polynomial. P of x equals 2x to the fifth minus 4x to the fourth minus 3x squared plus 1. And then also B, the polynomial Q of x equals negative 3x fourth minus 3x cubed plus 5. So in our first polynomial, polynomial A, the degree of our polynomial is odd because it's a degree 5. And the leading coefficient is positive. So that means that our left tail is down and the right tail is up. On our second polynomial, we have a negative leading coefficient, and the degree of our polynomial is even because it's 4. So that means that both tails are down. We also have something called a relative extremum, and that is a point where the graph reaches a minimum or maximum compared to the other points nearby. So in general, an nth term degree polynomial cannot have more than one less than the degree of relative extrema. So whatever the degree is, you can't have, they're never going to have more than one less than that. Since complex roots do not correspond to x-intercepts and are not graphed on the real number line, some polynomials have even less than n-1 relative extrema. So if you have a degree 5, you can't just say, oh, it's going to have 4 extrema because that's 5 minus 1. Well, that might not necessarily be true because you can have some complex roots. You just know it's going to have less than 5. So let's talk about using all of these characteristics to graph a polynomial functions. So 1, we want to plot the zeros and consider their multiplicities. So this is what all the lessons beforehand have been helping us do. You know, factoring and then finding the zeros and finding the multiplicities of those zeros. Those are going to help you plot the zeros. And then we're going to consider the tails based on the degree and the leading coefficient, which we just went over. And then we're going to take advantage of symmetry. If you have an even degree, you're going to have symmetry across the axis of symmetry. If you have an odd, you're going to have point symmetry. After that, you're going to plot the y-intercept and any other strategic points that we know of, and then we'll sketch the curve. So let's graph x cubed minus x squared minus 2x and give the domain and range. So first of all, we want to find the zeros. So we'll go ahead and factor out an x, and then we'll factor that x squared minus x minus 2, which means that our zeros are 0, 2, or -1. So we can go ahead and plot those. We know that it is an odd degree because it's a degree 3, and it has a positive leading coefficient. So that means that the left tail is down and the right tail is up. There's no symmetry. So here's our zeros. So remember we said the left tail was down. So we're going to start going down. And then we know we have to come back. And then we have to make sure our right tail ends up going upwards. So our domain for all polynomials is always going to be the same, all real numbers. And then for our range for this particular polynomial is all real numbers because our left tail is approaching negative infinity, where our right tail is approaching positive infinity. So that means we're going both directions. So our range is all real numbers. Let's try another one. Let's graph x to the 4th minus 3x squared minus 4. So we need to find the zeros, so we're going to factor. So first of all, we'll factor, and we'll have x squared minus 4 times x squared plus 1. So which means that if we solve for both of those, we get x is equal to plus or minus 2, or x is equal to plus or minus the square root of -1, which is I. So it's an even degree and positive leading coefficient. So if it's an even degree, that means that both tails are either up or down. But since it's a positive leading coefficient, that tells us that both tails are up. So all terms have an even degree, which means that we're symmetric across the y-axis. We also have a y-intercept of 0, -4. And we can find some symmetry. Let's say we plug in 1, we get -6. And then so by symmetry, that means that 1 gives us -6, which means -1 will also give us -6. Okay, so here are our zeros. We cannot plot the plus or minus the square root of -1. Those points can't be plotted. However, the other points that we plotted can be. So there we go. There is our graph. So our domain is all real numbers because it's polynomial. However, our range is not going to be all real numbers because it never goes below these points. So those are examples of relative extrema. Those are the minimum points, right? Like nothing ever goes below those points. And that point happens to be negative 6.25. So our range has to be bigger than those numbers. All right, let's graph x cubed minus 4x squared minus 3x plus 12. This one we can use synthetic division and our rational root theorem to get our zeros. So 4 ends up being a good number to divide by using synthetic division. Means that one of our roots is x minus 4. And when we do that, it leaves us x squared minus 3 as our, after we divide using synthetic division, we end up with x squared minus 3. And we can set x squared minus 3 equal to 0. And that means that we get x minus the square root of 3 and x plus the square root of 3 for our other factors. Which means that our zeros are 4 and then plus or minus the square root of 3. Our polynomial is an odd degree because it's degree 3 and it has a positive leading coefficient, which means the left tail goes down and the right tail goes up. Since our polynomial has even and odd exponents, there's no symmetry. We do know that our y-intercept is 0, 12. Remember, to find the y-intercept, we let x be 0. So the y-intercept is sometimes easy to find. So we're going to go ahead and plot our zeros. And then our y-intercept, 0, 12. And we'll mark some points of symmetry. Or not symmetry, but we'll plot some other points. And there we go. Here's our graph. So notice how our left tail was down and our right tail is up. All right, another example. Negative x to the 5th plus 2x cubed minus x. So factor by synthetic division. First of all, before we do that, let's go ahead and factor out an x to make it a little bit easier for us. And so now we're just dealing with this x to the 4th minus 2x squared plus 1. We actually factored out a negative x. So now when we use synthetic division, or we can either use synthetic division or we can just factor using the reverse box method. And we end up with x squared minus 1 squared, which means that this is difference of squares. It's x minus 1, x plus 1. And since it's squared, then those happen twice as well. Which means that we have our zeros x equals 0, x equals 1, x equals negative 1. However, 1 and negative 1 have a multiplicity of 2 because those factors happened twice. It's an odd degree because it's a degree 5 and it has a negative leading coefficient, which means the left tail is up and the right tail is down. All terms have an odd degree, so they're symmetric with respect to the origin. So if we were to plug in negative 1/2 and get this number, then if we plug in positive 1/2, we would have to get the same number. So that helps. So we'll plug in our zeros. And we'll plug in some symmetry numbers. And there is our line. So notice how the left-hand side was up, our left tail was up, and our right tail was down. So our domain is all real numbers, and since we're going up and down, we have our range is all real numbers. All right, those are all the examples. Go ahead and try some problems yourself.